In this lecture, we want to accomplish two things. First, we want to provide a brief overview of cloud computing. In this overview, we want to explain the technical ideas behind cloud computing, as well as the motivation for this paradigm. This explanation is not intended to exhaustively cover cloud computing. We simply want to provide an overview so that we can focus on the real purpose of this video: security concerns related to cloud services. Thus, with a general understanding of cloud computing, we can address the second objective of this video, the discussion of security issues that are unique to the use of cloud services. Let's begin by providing a definition of cloud computing. We'll start with the NIST definition. The National Institute of Standards and Technology provides a definition of cloud computing through special publication 800-145, which was published in the year 2011. In this document, NIST states that cloud computing is a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources, which will include networks, servers, storage, applications, and services. These computing resources can be rapidly provisioned and released with minimal management effort or service provider interaction. The model that they suggest is composed of 5 essential characteristics which we could consider features of cloud computing. 3 service models that address capabilities provided to consumers, and 4 deployment models which describe how resources can be made available to consumers. This document was published in 2011 as cloud computing was essentially just getting underway. As such, NIST notes that cloud computing is an evolving paradigm. Although published in 2011, we can say with some confidence that describing it as an evolving paradigm is accurate even today. This has led to the fact that cloud computing may be subject to different interpretations. Let's look at the essential characteristics. The NIST cloud model includes 5 essential characteristics. First, there's on-demand self-service. A consumer can unilaterally provision computing capabilities such as server time and network storage as needed automatically without requiring human interaction with each service provider. Broad network access. The capabilities are available over the network and accessed through standard mechanisms that promote use of heterogeneous thin and thick client platforms, such as mobile phones, tablets, laptops, and workstations. We've used a couple terms which may not be familiar to you, so let's provide a little background. In a client-server environment, we say a client is a front-end device through which the user interacts with some service provider. In a client-server architecture, processing can be distributed between the clients and the server. A thick client, also called a fat client, is one that performs much of the processing of an application. What we might refer to as business logic is addressed by this client. With a thin client, the bulk of the processing is accomplished on the server. This client might do little more than render a user interface. That is, no business logic is performed on this type of client. Resource pooling. The provider's computing resources are pooled to serve multiple consumers using a multi-tenant model with different physical and virtual resources dynamically assigned and reassigned according to consumer demand. Customers generally have no control or knowledge over the exact location. This is the notion of location independence. Examples of resources would include storage, processing, memory, and network bandwidth. Rapid elasticity. Capabilities can be elastically provisioned and released to scale rapidly outward and inward, commensurate with demand. To the consumer, the capabilities available for provisioning often appear to be unlimited and can be appropriated in any quantity at any time. Measured service. Cloud systems automatically control and optimize resource use by leveraging a metering capability at some level of abstraction appropriate to the type of service. Resource usage can be monitored, controlled, and reported, providing transparency for both the provider and consumer of the utilized service. The NIST cloud model includes 3 service models. Software as a service. This refers to the capability provided to the consumer to use the provider's applications running on a cloud infrastructure. Applications are accessible from various client devices through either a thin client interface, such as a web browser, for example, web-based email, or a program interface. The consumer does not manage or control the underlying cloud infrastructure, including network, servers, operating systems, storage, or even individual application capabilities. A possible exception would be limited user-specific application configuration settings. Platform as a service. The capability provided to the consumer is to deploy onto the cloud infrastructure consumer-created or acquired applications created using programming languages, libraries, services, and tools that are supported by the provider. The consumer does not manage or control the underlying cloud infrastructure, but has control over the deployed applications and possibly configuration settings for the application hosting environment. Infrastructure as a service. The capability provided to the consumer is to provision processing, storage, networks, and other fundamental computing resources where the consumer is able to deploy and run arbitrary software, which can include operating systems and applications. The consumer does not manage or control the underlying cloud infrastructure, but has control over operating systems, storage, and deployed applications, and possibly limited control of select networking components, for example, host firewalls. And the NIST cloud model includes 4 deployment models. Private cloud. The cloud infrastructure is provisioned for exclusive use by a single organization comprising multiple consumers or business units. It may be owned, managed, and operated by the organization, a third party, or some combination of them, and it may exist on or off premises. Community cloud. The cloud infrastructure is provisioned for exclusive use by a specific community of consumers from organizations that have shared concerns such as mission, security requirements, policy, and compliance considerations. It may be owned, managed, and operated by one or more of the organizations in the community, a third party, or some combination of them. And again, it may exist on or off premises. Public cloud. The cloud infrastructure is provisioned for open use by the general public. It may be owned, managed, and operated by a business, academic, or government organization, or some combination of these. It exists on the premises of the cloud provider. Hybrid cloud. The cloud infrastructure is a composition of two or more distinct cloud infrastructures, private, community, or public. These remain unique entities, but are bound together by standardized and proprietary technology that enables data and application portability. A major benefit of cloud computing is that organizations do not need to purchase their own hardware to provide services for their users and customers. An enterprise is able to purchase access to hardware resources according to its demands and without upfront costs. If demands decrease, the enterprise can decrease the amount of remote hardware resources for which it is paying. If demand increases, the enterprise can easily adjust the resources to the new demand. Cloud computing isn't a single concept. Different cloud providers provide different services. For infrastructure as a service, we have low-level services like virtual machines, which can be booted with a user-defined disk image. An example is Amazon EC2. For platform as a service, the cloud providers offer an API, a programming interface that can be used by application developers. An example of this is Google's App Engine. For software as a service, services most useful for end users, such as web-based office applications, are available. For example, Google Docs and Calendar. The main idea of cloud computing is to outsource the management and delivery of software and hardware resources to some cloud provider which specializes in that particular service and can provide much better quality of service at lower costs in a convenient fashion. So cloud computing is concerned with moving services, computation, and data off-site to either internal or external centralized facilities. The location of such a facility is essentially transparent to users of the resources. This allocation or distribution of resource is motivated largely by economic factors, the reduction of overhead costs. However, other motivating factors have also been attributed to this movement of resources, including opportunities for enhanced collaboration and integration of services. Possible benefits of cloud computing include, but are not limited to what we present here. Resource coupling. In cloud computing, the resources available are loosely coupled. That is, the resources are less dependent upon each other. Scalability. If additional capacity and resources are required, the service provider will provide these. The consumer need not purchase or install additional resources at their location. When these resources are no longer needed, the provider reallocates them. The consumer pays according to usage. Reduce costs. Consumers run applications at lower costs because they do not need to purchase additional hardware. Pay per use. With cloud computing, consumers pay according to usage and do not incur upfront costs. Automatic updates. Access to updates of software may be included with a cloud computing service. With some background provided here on cloud computing, let's now consider some security risks that may exist within this environment. We'll consider three classes of risk. Traditional security threats. These are threats experienced by any system connected to the internet, but when dealing with a cloud-based platform, there are some specific twists that arise. Threats related to system availability. System failures, power outages, or other such events can cause a shutdown of cloud services for extended periods of time. And finally, threats related to third-party data control. These are threats that relate to a range of concerns caused by transparency and limited user control. The traditional threats begin at the user site. The user must protect the infrastructure used to connect to the cloud and to interact with the application running on the cloud. This task is more difficult because some components of this infrastructure are outside the firewall protecting the user. Authentication and authorization process. The procedures in place for one individual do not extend to an enterprise. In this case, the cloud access of the members of an organization must be nuanced. Individuals should be assigned distinct levels of privilege based on their roles in the organization. It's also non-trivial to merge or adapt the internal policies and security metrics of an organization with those of the cloud. Traditional types of attack have affected cloud service providers. These include distributed denial of service, phishing, SQL injection, and cross-site scripting. Cross-site scripting refers to a type of computer security vulnerability found in web applications. Such attacks enable attackers to inject client-side scripts into web pages viewed by other users. Now consider threats related to system availability. Cloud services could be unavailable for extended periods of time due to catastrophic events such as system failures or power outages. Tied to this is the concept of what is called data or vendor lock-in. The vendor lock-in problem in cloud computing refers to the situation where customers are dependent or locked in on a single cloud provider technology implementation. They're unable to easily move in the future to a different vendor without substantial costs, legal constraints, or technical incompatibilities. The lock-in situation is evident in that applications developed by specific cloud platforms, such as Amazon EC2 or Microsoft Azure, cannot easily be migrated to other cloud platforms, and users become vulnerable to any changes made by their providers. So the lock-in issue arises when a company, for instance, decides to change cloud providers or perhaps integrate services from different providers, but is unable to move applications or data across different cloud services because the semantics of resources and services of cloud providers do not match or align with each other. And another issue related to system availability is that users cannot be assured that an application hosted on the cloud will return correct results. Recall that the concern with respect to third-party control relates to a range of concerns caused by transparency and limited user control. Specifically, there is user concern regarding the legal framework for enforcing cloud computing security. A cloud service provider may outsource the handling of personal and/or sensitive information. So cloud security and privacy legislation has not kept pace with the advancement of cloud technology. This misalignment has raised concerns of users regarding the ability to defend their rights. Consider that the data centers of a cloud service provider may be located in several countries. Earlier, we had mentioned location independence as a characteristic of cloud computing. However, this characteristic makes it difficult to understand which laws apply. The laws of the country where information is stored and processed, the laws of the countries where the information crossed from the user to the data center, or the laws of the country where the user is located. A cloud provider may subcontract some resources from a third party whose level of trust is questionable. There are examples when subcontractors fail to maintain the customer data. There are also examples that can be found when the third party was not a subcontractor, but a hardware supplier, and the loss of data was caused by poor quality storage devices. Existing laws stating that the cloud provider must exercise reasonable security may be difficult to implement in a case where there is a chain of outsourcing to companies in different countries. Another concern for the user is that a cloud service provider may be required by law to share private data with law enforcement agencies. The storing of proprietary data on a cloud is potentially risky because cloud provider espionage poses real dangers. And the control over the life cycle of data is somewhat difficult. A cloud user may not be able to prove that data has actually been deleted by the service provider. If we're performing an operation where we're doing data manipulation, insert, update, delete, and we say, let's remove some data, is there some absolute guarantee or confirmation that such data has been deleted by the service provider? Additionally, the physical devices on which the data had been recorded, have they been wiped clean? Simply deleting an entry in a control structure that says, okay, the file no longer exists, is not the same as physically removing the actual representation of the data from the storage device. So the terms of contractual obligations usually place all responsibilities for data with the user. The Amazon Web Services customer agreement, for example, does not help boost user confidence. It states, for example, that we will not be liable to you for any direct, indirect, incidental damages, nor will we be responsible for any compensation, reimbursement arising in connection with your inability to use the services. the cost of procurement of substitute goods or services, or any unauthorized access to, alteration of, or deletion, destruction, damage, loss, or failure to store any of your content or other data. Consider what cloud users can and should do to minimize security risks regarding data handling by the cloud service provider. These users should evaluate the security policies and the mechanisms the cloud provider has in place to enforce these policies. Users should analyze information that would be stored and processed on the cloud. The contractual obligations should be clearly spelled out with the contract between the user and the cloud service provider, and these should address such things as stating explicitly the provider's obligations to securely handle sensitive information and its obligation to comply with privacy laws. It should also spell out the provider liabilities for mishandling sensitive information and the liabilities for data loss. It should spell out rules governing ownership of the data. And it should also specify geographical regions where information and backups can be stored. So to minimize security risks, a user may try to avoid processing sensitive data on a cloud. When the volume of sensitive data or the processing workflow requires sensitive data to be stored on a public or hybrid cloud, then, whenever feasible, data should be encrypted. Note, however, that this poses a bit of a challenge as well, because encryption prevents the indexing and searching of the data. One other concern is virtualization, say the use of virtual machines. Virtualization is at the forefront of cloud-hosted services. It involves machine consolidation, where multiple application servers are co-located on the same physical machine. Through virtualization, we cleanly decouple the administration of hosted software from that of the underlying physical hardware. A benefit to virtualization is that it allows customers to provision servers quickly. Multiplexing several virtual machines onto a single physical host allows cloud operators to provide low-cost, least computing to users. Managing virtualization is not a trivial task. There are complexities associated with the administration of such environments. Thus, with the use of virtualization, customers must trust the provider to kind of get it right, and are often helpless should the provider fail in successfully administering the environment. Users rely on the provider for both the availability of resources and the confidentiality of the user's data, making critical both the security and the availability of the systems. Right? The specific areas of concern with respect to cloud security include computational resources being off-premises. Because these resources are off-premises, enterprises do not have the same amount of control over their resources and their data. In fact, in most cases, they have no guarantees over the level of security and protection of the resources they manipulate. Another area of concern is the use of compromised software. An enterprise might purchase access to an operating system that has been compromised in some way by an adversary who can steal its data and interfere with the computation. Additionally, location and legal issues are a concern. Company data might be stored in a different country where laws governing data ownership might be different from what the company expects. For example, a European company that decides to store its database with a cloud provided in the US might discover that its data would be subject to inspection because of the US Patriot Act. Lack of industry regulation is another concern. The cloud computing market is unregulated, and the service level agreements between cloud providers and cloud consumers are often vague. As a result, it's very difficult to hold cloud providers liable for security breaches. And the final concern we mention is the lack of transparency and trust. Cloud deployments require an unprecedented degree of trust on the part of users in terms of both the intention and competence of service providers. Cloud providers, for their part, offer little transparency or reason for users to believe their trust is well placed. So in the cloud, multiple virtual machines run on the same infrastructure, which will cause some potential security risks. Cloud is a shared environment, and data in the cloud is not as secure as it might seem. The storage location of data within the cloud is unknown to users, and cloud providers may have access to such data without proper authorization. Virtual machines may access data on other virtual machines and the same infrastructure without proper isolation and configuration. This again was the point we were making about the complexity of managing virtualized environments. Cloud computing has fundamentally changed the way people view computing resources. Rather than being an important capital consideration, they can be treated as a utility, like power and water, to be tapped as needed. Offloading computation to large centralized providers gives users the flexibility to scale available resources with changing demands, while economies of scale allow operators to provide required infrastructure at lower cost than most individual users hosting their own servers. However, these benefits come at a potential cost to the user.